As we begin Algebra 2, I will tell you that Algebra 2 is nothing more than a rework of Algebra 1. So most of this stuff should be familiar at some level, and it may look a little bit more challenging because we're using fractions and decimals and those kind of things, or different functions, but it is a review basically of Algebra 1. So what are we going to talk about? Let's see, we're going to determine whether functions are one-to-one. We're going to talk here about, in functions and continuity, talk about continuity, the domain and range of functions. Hopefully that is familiar. Some of the key words, I've crossed off some stuff that we are not going to necessarily talk about. This is supplementing our classroom instruction, and so that's why some things may or may not get mentioned, because we focus on them in class, or I'm going to omit things because it's just not necessary for what we're covering. Functions, the domain of a function. The domain in the function is going to be what are all of my x values. So thinking about this, the domain is going to be anywhere it exists along the x-axis, right? So this function goes on forever and ever, down and to the right, and then down and to the left. So technically it does go forever and ever to negative infinity and positive infinity on the x-axis. So the domain is going to be, I'm just going to say all real numbers. Now the range, on the other hand, the range starts at y equals 0. So it doesn't exist in any y positive numbers, but it does exist going down to the negative. So it's going to be, the range is going to be my y values, and they exist from y is less than or equal to 0. And that is understanding the scope of my y and x intercepts, or y and x axis, the values indicating domain and range. And I will say that your ordered pairs on the coordinate plane are x, y, and then if you think about it in alphabetical order, you have domain and range. So my domain is always going to be the x values, the range is going to be the y values. Let's see here, horizontal line test, that's often something we talk about. If it passes, horizontal line test is a sign of a function, because it doesn't repeat itself. We have one input, one output. So hopefully that is a familiar thing from Algebra 1. So I had to modify this question a little bit. So, but what is the domain of this function? If I were to exaggerate this function, it goes on forever and ever, down and to the left, down and to the right. So the domain is going to be, again, it is going to go forever to the negative to a negative infinity and positive infinity. So again, my domain of this function is going to be all real numbers. If you wanted to look at the range, of course, is going to be a maximum of y is 3, and then it would be everything less than. So my range would be equal to y is less than or equal to 3. So different things that we have to be thinking about. Let's see here, analyze the functions and give the number of gold and silver medals that give the number of gold and silver medals won in a particular year, and define the domain and range of each function and state whether it is one-to-one or both or neither. Let's just think about the function. F of x is the function that gives the number of gold medals won in a particular year. The domain is the year. Here is my input, here is my output. So what they're saying is this is my domain. These would be my x values, right? And then my gold medals would be the number of gold medals that were presented in that year. It is not necessarily a function because over 2 years we had the same number of medals. So it isn't that one-to-one. So in 2016, we received my x, here's my x and my y repeated itself here, and my y repeated itself here. So thinking of that one-to-one, or that function, the input, I like to think of it as a soda machine or any kind of vending machine. If I put my money into the vending machine and I press B7, and B7 is for a Sprite, I expect a Sprite to come out. That is a function. I put my money in, I press B7, and I get out a Sprite. If, however, when I pressed B7, I get out a Coke, then something's wrong, because I'm expecting to get a Sprite. So that is, when I put one thing in, I get one thing out. So if I were to get a Coke instead of a Sprite, there's something wrong with that function. So that's why they're saying that in 16, I got out 46 metals. In 12, I got out 46 metals. So it wasn't the one-to-one they're looking for. We'll cover more in class. So again here, the domain of each function is one-to-one both, or let's just worry about the domain of this function passes my horizontal line test, and let's see here, the function is a one-to-one function. Let's see, what else are we looking for? The graph indicates that the domain is all real numbers, and the range is y is less than or equal to -4, okay? Because here is where my range starts at 4, so my range is y is less than or equal to -4, and then because this function goes on forever and ever to negative infinity and positive infinity, that's why they say my domain is all real numbers, okay? Functions, talking here about discrete and continuous functions. Functions can be discrete, continuous, or neither. So real-world situations where only some numbers are reasonable are modeled by discrete functions. Situational where all real numbers are reasonable are modeled by continuous functions. And I think of a continuous function is if I were to pour water out of a pitcher, right? I can dump water and stop and start and stop and start and just drop just the tiniest little bit of water, or I can pour the whole pitcher out. It's a continuous flow, where I think of a discrete function as eggs. If I have a dozen eggs, then I can't have a portion of egg. It's sort of like I have one egg, I have 2 eggs, I have 3 eggs. I can't necessarily serve up, or I can't have 1.5 eggs, because then my shell doesn't work out and those kind of things. So just thinking of discrete as something that I can define. It's a discontinuous function, and the points are not connected. So it's something that I can sort of count. So here, looking at these functions, this is an example of a continuous function because it doesn't stop. Okay, this is considered the function is neither. So let me go ahead, determine whether these functions are discrete, continuous, or neither. So this is continuous. This is not continuous because I have this little hole in the function right here. X can never be 2. X will never be 2 because there's a hole in the function. So that's why it's not continuous. And discrete, it's not discrete because it actually continues on in the rest of the function. And now here is an example of a discrete function where I just have these items, that are present. So it's made up of those distinct points. The domain in this case, the domain is going to be the x values. For example, this point right here is 3, 2, and 3 is part of my domain, and 2 is part of my range. Okay, so looking at that. Determining continuity. Determine whether the function that models the cost of coffee beans is discrete, continuous, or neither discrete nor continuous, and then state the domain and range of the function. Discrete. Up to, let's see here, continuous. Up to 2 pounds, it's $8 a pound. So we have a continuous function up to 2 pounds, because I can stop at a half pound, I can stop at 3/4 of a pound, I can stop at 1.5 pounds. So it is continuous up to 2 pounds over the interval from 0 to 2. And then it becomes discrete, because then I don't have a continuous, like for example here, I cannot purchase coffee that is 2.25 pounds. Once I hit 2 pounds, then I have to have increments of 2.5, 3, and 5. So it becomes a discrete function. So it is neither continuous nor discrete. It is actually, okay, we're going to talk about it both. So that's what they're talking about here and thinking of those functions. Let's see here. Looking at the domain and range again, the domain of that function was 2 pounds, up to 2 pounds, right? Up to 2 pounds. 2.5, 3, and 5. That was the domain. And then the range would be the cost, right? So I put in a certain pound of coffee, I get out a cost. So that is my input, output of the function. Here, let me see here, set builder and interval notation. This is hopefully a review for you guys from most of your math classes. Algebraic notation sets are described using algebraic expressions. X is less than 2, right? Because it's an open circle over the 2, so it continues on forever in negative infinity, so X is less than 2. Set builder notation would be presented much like this, that for all values of X such that X is less than 2. Okay, so that's what we're talking about. And they're saying here that this little bar is read as such that. Interval notation is listed from, we read this, the interval is from negative infinity to 2. And if you'll notice, we have parentheses here. Parentheses on interval notation indicate that the value is not included. So if you see in our example that 2 is an open circle, that means 2 is not included, so we give it a parentheses. And it goes on forever to negative infinity. It never touches infinity or negative infinity, so that's why that gets a parentheses also. Using these as some examples here, this is 4, so X is greater than 4, or something like X such that X is greater than 4, and or interval notation would be 4 parentheses, because it doesn't touch the 4, and then it continues on forever in a positive direction. For this next example, we have X is less than or equal to 4, because it is included, it has the dot filled in, which would mean such that X such that all values of X that are less than or equal to 4. And then now, since it touches 4, we have negative infinity, the interval notation, up until 4, and since 4 is included, it would have a bracket. And then here in this final example, we are somewhere between 1 and 5. And then, of course, it would be something along the lines of all values of X such that 1 is less than X, which is less than 5. No, that's not right. Is it X? No, that was right, sorry. And then also notation would be simply 1, 5, both in with parentheses because it doesn't touch the 5. So there are some of my notations. And again here, the domain of this function, the domain and range, and set builder and interval notation. Set builder, the domain is all real numbers because it goes on forever, positive and negative. And then in parentheses, we would have negative infinity to positive infinity. The range starts at -6 and goes upwards. So we have y such that y is greater than -6. I don't know why we didn't include it. We could probably have included it and it would have been okay because it should. It looks like it touches 6. And then right here I have brackets indicating that -6 is included and it goes on forever to positive infinity. So that is talking about my general set builder review. Take a moment here for these. Okay, so I'm just looking here real quick that the domain is x such that x is all real numbers because it goes on forever and ever in both directions. So we have parentheses, negative infinity, positive infinity, parentheses. The range starts at 3 and then goes to negative. So y such that y is less than or equal to 3. And then therefore we have open parentheses to negative infinity and brackets at 3. And I will just say here that domain and range are both all real numbers. And then we would have the parentheses for our interval notation. So set builder interval notation here, what we're talking about it is there are breaks in its continuity. So we know that write the domain and range and graph in set builder notation. So here the domain is, I like the interval notation, it's a little bit easier. The domain goes from negative infinity to -1, but it does not include -1. And then it has the union of 0 to positive infinity. 0 is included because of the solid dot. Then the range is going to be similar. The range goes from negative infinity to -1, but -1 is not included. So negative infinity to -1, or y such that y is less than -1, or the union. We have 2. Y is 2, and it is included, and it goes to all things positive infinity. So there you go. There's a good example to look at for set builder notation. And then talk about linearity, intercepts, and symmetry. Okay, so linear functions. No variable is raised to a power other than 1. Some of the big, and it says here the linear functions mx plus b, that is that slope-intercept form. You have your standard form of a linear equation. Basically y equals x is the most basic linear function we have, or linear equation. And the function that is not linear is called a nonlinear function. And the graph of a nonlinear function includes all sets that just do not lie in the same line. So identifying these functions, are they linear functions? Here we have x to the first power. When they simplified it, we simply have 2x to the first power. So yes, that is a linear function, whereas this next one is x to the third power. So ultimately it is shaped something like that on the coordinate plane. So that is not a linear function, does not form a straight line. Let's see what else here. We have linearity. This is actually a absolute value function. It is not linear. Then it's this one here. All my points seem to be on the same line. So yes, it is a linear function. If we were to graph these functions over here, just some as example, this function would look something like this. Hopefully you remember what a parabola and a quadratic function looks like. That is considered nonlinear. This function would probably look something like that, and that is also nonlinear. And then this absolute value function looks something like that, and it is nonlinear. So just understanding what these functions look like, because we are going to talk about second and third degree functions a lot, so being aware of that. Linear functions from a table. We know that a linear function has a constant rate of change, right? Thinking about y equals mx plus b, right? M is my slope. So we have a constant rate of change. So you can take some points here and determine what is the slope, the change in y over the change in x. When you're presented with a table like this is always going to be x, y, unless they tell you otherwise. The same thing if you have a table that is vertical, you will have x, y data. So as we look at this, we can do the ordered pairs, or I can see how much am I changing by. But let's just take 2 points using my y. We'll call this y2, y1, x2, x1. So I went ahead and did the slope formula, and I came up between these 2 points a rate of change of 34, and I went ahead and checked again for another set of points, and the rate of change between those 2 points was also 34. So I do have a constant rate of change, which indicates a linear function. Here, intercepts and graphs, understanding what intercepts look like. X-axis and x-intercept. X-intercept is where does it cross over the x-axis, and this function crosses over the origin, which happens to be the x-axis and the y-axis happen to both be 0. Understanding and finding intercepts on nonlinear functions. This is considered my y-intercept because that is where it crosses over the y-axis. This is an x-intercept, an x-intercept, and an x-intercept. So that is understanding what the intercepts are. -3 is my x-intercept, -1 and 2, and then of course 12 appears to be my y-intercept. Okay. So looking at this, estimating your x and y-intercepts of each graph, it looks like my y-intercept in this graph is 2. And my x-intercept is 1, 2, 3, 4, 5, -5. Looking at this other graph, my y-intercept looks like it is probably the origin or 0. And then my x-intercepts are going to be -4, -2, 0, 3, and 5. So those are my possible x and y intercepts for these 2 functions, and need to be able to understand those and recognize those, and we'll talk more about when it comes to positives and negatives, but understanding what those are, what's going on with those. So again, presented a function or a table, we have x, y. So interpret the meaning of the intercepts. So Ricardo launches a rocket from her balcony. The table shows the height of the rocket after each second of its flight. So right here we started off 0 at 15 feet, because that's what that height is. So this would be the y-intercept right here. This is my y-intercept, because that is where I started on the y-axis, and then she launched a rocket, and it came down and hit right there after 8 seconds. The height was 0, which is considered my x-intercept. So the table shows the x-coordinate when y equals 0 is 15, thus the y-intercept is 15. When x is 0, the table shows the y-coordinate when x is 0 is 8. Got those backwards. When y is 0, the x-intercept is 8. When the x is 0, the x-intercept is 15. The y-intercept is 15. So there you go. The x is the input of time, and the height is a product of how long have we traveled. So input, output. Symmetry, lines of symmetry and point symmetry. This is similar to, you have a line of symmetry, which we can fold in half, much like we were talking in geometry. Lines of symmetry and point symmetry is sort of like rotation. So they're saying that here we have a line of symmetry for a quadratic function, But here we do not have line symmetry. We have rotational symmetry or point symmetry, because if I were to rotate it around the origin, it would come back on itself. So that's what they're talking about there. Looking at these things that you know that functions that have line symmetry with respect to the y-axis are called even functions. Even functions, and then functions that have point symmetry are odd functions because of their shape, and they can be spun around the origin and come back right on themselves. So there are tests for it. We will go over that in class, but basically if every x of the domain, if the negative x and x equal, it's a even function. If the negative x and negative f of x are the same, then it becomes a odd function. So we'll get some practice with that, but do we have a point that we can identify the type of symmetry if we were to rotate that around? Do we have a point that we could rotate it from? We are talking about the origin, and the origin does not help us on this first one. On the second one, we do have a line of reflection, so x is -2 would give me a line of symmetry. Let's see here, if I were to rotate around that, I think we do have some form of rotational symmetry on our linear functions, because it would rotate back around and touch it and become itself again. There's no symmetry here because I can't draw a line down the middle and fold it in half. And then if I were to rotate 180 degrees about -2, then I would have 180 degree rotation, and that would be at 0. -2 would be that point which I could rotate around. And then identifying even and odd functions, again doing that test. I've worked out some of the formulas over here, and they're in your notes, but being able to do that test, now I can look at this function and I could say that's odd. If I were to rotate that around, it would fall back on itself. I can look at this function, I can say it is even because I have this line of reflection. And then this one again looks like it is probably an odd function, but we may not know for sure, because if you look, when I'm at -1, I'm a little bit above 2. When I'm at +1, I'm a little bit below 2, so that one does not match up. It appears it's really close to being that one, but if you look here at 1, I'm at -3. Here at -1, I'm at 3. So that's the difference between being able to quickly identify an even or an odd function based on its appearance. So with that, big review from Algebra 1, and we'll have to start applying some of this information.